Hello. Yeah. Okay. Good afternoon, everybody. So I will be talking something new uh, in this session, which has not been talked about much in previous sessions. Is I will talk about mostly about astrophysics. Okay. And the title of my talk is the strange case of twin neutron star. So what do we mean by twin neutron and star? We will be going through that. So before I start my talk, just thanking you all for inviting me. Uh, and let us start what do we know about and what the things that I'm talking about. So first I will talk about neutron stars. Neutron stars were uh, first theorized by Bede and Zwicky just after the discovery of neutrons. However, their observational counterpart were the pulsars were discovered much later. Okay, so here are the different properties of a neutron stars. And neutron star mass can range between this zero point 0.7 to 2.4 solar masses, radius around 10 to 15 kilometers, period from very fast to not that fast, and density of the core is extremely high and also high magnetic field. So, and this is a model diagram of a neutron star. So this is it is rotating about this axis, and this is its radiation beam or magnetic axis. So if I'm sitting here, I will observe pulses like a lighthouse effect, and therefore it was named this pulsars. So mostly the interesting thing is, so this mass and radius makes the density at the core very high, which is something very interesting, and we'll come to know in the later what it does. So to solve this thing, because they are so dense, that normal relativistic calculations will not apply. So what we have to do is we have to solve the Einstein equation, and this was done again in the early 30s. Tolman, Oppenheimer, and Volkoff came up with this equation. This is basically this hydrostatic equilibrium condition. This is the condition, and these two are the special relativistic terms, and this is the general relativistic term which comes as a correction. So this is a TOV equation. So this TOV equation you see will need an information about P and rho. That means the pressure and the energy density. And if we know the relation between pressure and energy, we can solve this equation, these two equations, to get the mass and the pressure. So this is, we start with some certain energy densities. Correspondingly, we have to have some pressure, and as we go outward in dr, the pressure decreases, energy density decreases. However, the mass increases. At this point, this is where the pressure is almost goes to zero, energy density goes to zero. It is called we define the radius of that star, and the mass where it saturates is called the mass of the neutron star. One thing that is important is we have to know how the pressure and energy density connects. Okay, that information comes from the equation of state. However, the equation of state that are viable here are extremely non-trivial, because at extreme densities we don't know the equation of state there. So that is one of the challenges of solving this, because this part of the equation of state of the pressure versus energy density, the relation between the thermodynamic variables are missing. So at this point, the current knowledge is that we know the equation of state with a great degree at this till the nuclear one time nuclear saturation densities, and also at very high densities, asymptotically high densities, because of this PQCD calculations. However, in the intermediate densities, we don't have any information. So what to do about? So there are many ways to proceed, and some people do this micro calculations of different models and all those things. However, in this talk, I will just do something which is quite different. Is that these are the points that we know, right? In the low density, and these are high density, and we know that the speed of sound is bound by this thermodynamic stability at 0 and causality at 1. I will randomize the speed of sound, okay, and obtain some points. These are randomized points, and then I will do an interpolation method, okay, in this way as a function of I will get speed of sound as a function of chemical potential by this interpolating method in this method, and then once I have no speed of sound and the chemical potential, I can calculate all the other things. So once I do that for first random choice, I will get a single curve. I can repeat this a lot of time, maybe a million times, depending on my strength of my computer or the supercomputing facility that I have. I will get all sorts of curve. So this is one of the equation of state. So this is the one of the equation of state which satisfies all the thermodynamic and all those bounds. So corresponding to this equation of state, what I will get is a mass radius curve. Be careful that this curve, in this curve, there are these are, let us say this, take us this particular curve. Each point on this curve is a neutron star with a certain mass, total mass, and certain radius. So these are all different masses. So corresponding to a equation of state, we get a one-to-one correspondence of this equation of state. So this different, but we can repeat this, right? I have said that we can repeat this continuously, and for different, we'll get all sorts of equation of state. It is not exhaustive. We can have an exhaustive equation of state. So this is some of the typical equation of state that one can get. So however, what is the actual equation of state is still not clear, but we have astrophysical bounds which has put several constant on the equation of state, and many of the equation of state has been rejected. So because the bounds are this, it has to produce two solar masses which the pulsar has been observed with a certain radius and all those things. So we are in a better state now, but still a lot of things need to be done. However, for this case, you have seen that this is a smooth equation of state. However, we know that this is not the only choice. We can even have a first order phase transition. Okay, so first order phase transition is, that is, there is a discontinuity jump in the energy density or the number density, but the pressure of the chemical potential is continuous. So if I have the first order phase transition, I can again construct a numerous equation of state. Okay, and this is how this first order phase transition, this is the transitions point of different strength, and it can originate from a different point of this is the phase transition point where it is happening. So these are different type of equation of state. If I have this type of equation of state, then my equation of state diagram is completely different. This is different from this one. This outline is the smooth equation of state, all the ensemble of smooth equation of state that we have. However, if we have a first order phase transition, you can see this ensemble changes. Okay, and we have constructed this. So what is the specialty about this, or what is the thing about this? Is certain things that comes up is the twins. What are twins? You know that I am referring to twins in this case is that these three are of, you can see their volume, shape, height, and all those things are different. However, their masses are same. In my definition of twins, I will just adhere to this, and I will define twins in a certain way. So what I am talking about, a specialty of twins is that in some cases where we have constructed this discontinuous for different discontinuous thing, what I can get in some cases is that this mass radius curve can increase and then decrease. This decrease is the instability line, unstable points, because at this point the gravitational, if you shift the if you give a small perturbations, the gravitational effect takes over and there is a collapse. However, this part is again stable. So let us say these 2 points. These 2 points you can see in this figure, and in this figure, these 2 points has same masses but different radius. So this is what I am calling a twin star. I am calling twin star this cases, same mass but different radius. Okay, so and because you can even see in this diagram that there can be different types of twin. One is if my mass radius curve can increase till here and then it can dip and then go up. These 2 stars can be twins, or it can increase till here and then goes down. Then these 2 stars are twin stars. So there can be different types of twins depending on how I construct my equation of state, and that is exactly what I have done. So these are different categories of twin, and I have defined a certain category 1, 2, 3, and 4. How I have done that is that I will say that category 1 twins are twins where these two masses at very high mass, this they have the same mass but radius is different. So these are category 1 twins. This has been categorized. This is the category 2 twin, where the first branch, this is basically the hadronic branch, it goes up till 2 solar masses, then it comes down, and here there is a stable point. These two stars are twin stars. These are called category 2 twin stars. We can have also this type of case, which I have shown earlier. This is the first hadronic branch. This is the second, let us say, quark branch, and these two stars have same masses. These are called category 3 twins. And this is a one extra special category, is that where the first branch doesn't go above 1 solar mass. Why is 1 solar mass? Because most of the stars, neutron stars measured till now, are above 1 solar mass, barring one pulsar, which is an Hess mass. So mostly these are my 4 type of twin star that I can have. And let us now examine how these twins are different from normal stars. Not only normal star, but different but stars which are formed from first order phase transition. What are the specialty about it? So how to differentiate them? How to filter out twins by measurement or by astrophysical measurement? So there is a thing that goes by the name of universal relation, is that this I, love, and Q. I is the moment of inertia, love is the love number, and Q is the quadrupole moment. Love number is basically a constant of proportionality. If we have a tidal field and our neutron star will have some, for this tidal field, the quadrupole moment of the neutron star can change, and this relation between this tidal field and the love number proportionality is the love number. Okay, so this has an interesting property, is that whatever equation of state you take, because I have previously told you that the equation of state are unique, right? Because given a equation of state, you have the different mass radius curve. Your mass, if you change the equation of state, your mass radius curve differs. However, if I take these 3 quantities and I make them dimensionless with a particular way, then this shows this is the black curve is the fitting parameter for all smooth equation of state. And then all this if I plot I versus love number, this lambda is the love number, then they fall in the same line. It doesn't matter what is the equation of state. It is independent of the equation of state. Therefore, it is called a universal relation. However, for twins, you can see that in twins, when it goes to the other branch, this universal relation starts to break. And it is more clear in the third category of twin, is that once there is an, so these are normal smooth equation of states. They follow a very universal relation. But suddenly, if once it goes to the second branch where the star can have a quark core, this universal relation starts to break. Okay. However, at very high densities and low densities, they again follow the universal relation. So this is one of the way of differentiating twins or first order phase transition from normal smooth equation of state. However, these are for only one equation of state. These are mass I and lambda for one equation of state. So what about if I plot them for all sorts of equation of state that I have constructed? Let us say 10,000, 50,000 equation of state. So see, this fit black curve is for a smooth equation of state. They doesn't show any deviations. They are very smooth, and they follow this polynomial. Okay, this fitting parameter, where these parameters are given here. However, if I plot the first order equation of state, they see that there is quite a significant variation. Okay, now the first order equation of state I have shown you depends on what is the density discontinuity that we have considered. Okay, delta epsilon, and also on the point of where the phase transition is happening. It can happen at very low densities, it can happen at very high densities, and we can see that the deviations depends on the delta epsilon. What is the density discontinuity? However, they don't depend much on the point of phase transition, because this different color shows where the phase transition is happening. There is no way of differentiating them. So normal first order equation of state depends mostly on the the deviations from the universality depends mainly on the density discontinuity. However, for twin stars, these are different category of twins. Green is the category 1, red is the category 2, and these are the category 3 and category 4. Here I have plotted again this I versus lambda and also this fractional percentage error. This shows how much it differs from this fitting parameter, and we can see that there is this category 3 and 4 and also category 1 and 3 differs. Then how to, let us check how they depend, whether this deviation from this fitting parameter for the twins either depends on the density discontinuity or where the phase transition is happening. So I can plot the maximum deviations as a function of the point of phase transition, and I can see that for category 3 and category 4, this maximum deviation is dependent on where it is happening. So the more earlier the phase transition happening, the more is the deviation. However, there is no such trend when I am seeing the maximum deviation as a function of the density discontinuity. Therefore, for normal first order phase transition, the deviation from universal relation depends on the density discontinuity. However, for twins, it depends on the where the phase transition is taking place. So this is a way of filtering out the twin equation of state, because twin equation of state has, yes, is the density discontinuity, the first order phase transition. Yeah. Okay. So this is one way of differentiating twin. Is there any other way? Okay. There can be, which is where I come into, is the binaries. What are the binaries? You have already know this curve is the gravitational wave from this 1708-17, where two neutron stars merged to give off gravitational wave, which was recorded in LIGO, Hanford, and Livingston. And Virgo was beyond the horizon of the Virgo, so it didn't recognize. So what happens in this binary merger is that two neutron stars merged to form a hypermassive neutron star. I will tell what is a hypermassive neutron star to give off gravitational wave, and ultimately it formed and rigged down to form a black hole. So what exactly happened is that these are the two neutron stars. They are inspiraling each other. They ultimately touched each other and collapsed. And one of the way of is that they can promptly, if the mass is very high, they can promptly decay into a black hole. However, if the mass is not sufficiently high, they can form this point B, which is the hypermassive neutron star. That means this neutron star is stable for few milliseconds. However, ultimately, once few milliseconds evolves, it can, because this is balanced by differential rotations, normal rotations. However, once this ceases, it again can collapse to a black hole or form a supermassive neutron star. A supermassive neutron star is stable for few seconds, 2 minutes. However, again, if once the rotation stops, it can again collapse to a black hole or form a normal neutron star. So this is the black hole formation. These are the different, depending on the mass of the two neutron star collapsing, we can have all sorts of final population. However, and in the gravitational wave side, this is the inspiration, the signal from the inspiral part. This is called the chirp signal. Okay, and this is the transient, is that this part, which is where all sorts of things happens, because they first touch each other, they have a lot of rotational velocities and all those things. But after it settles, after few milliseconds, 2 to 3 milliseconds, we have a constant, well defined amplitude and frequency. This is called the post-merger hypermassive neutron star signal, and ultimately it collapses to a ring. It rebounds to form a black hole. Okay, so this is for this part of this. So these are the gravitational wave signal. Now, so this was done previously. How do I help my case of twins with this? So to do this numerical simulations of this and analyze, we have to use again the general relativity, but now we have to solve it in computers, because this cannot be solved with analytical methods. So what in computers, what do I do? Because we know how to solve differential equations. Okay, so in differential equations, there are space dimension and time dimension are different. So what I can do is I can use numerical relativity, where there is a 3+1 formalism of exfoliation of 4-dimensional space-time to 3-dimensional hyperspaces and 1-dimensional time. Is that they this exfoliate space-time into different hypersurfaces, and these are the time direction in which they evolve. different hypersurfaces at different times. So there is an evolution of time. So, and this is how this exfoliation is done. Okay, so this has we go from a 4-dimensional metric from GAB to a 3-dimensional spatial metric gamma AB. We have a normal vector which takes it in the different evolution of time. We have this shift vector, which is this shifting in the hypersurfaces in the spatial dimension, and we have this lapse function which takes from one hypersurface to the other hypersurface in time. Okay, so once we do this, we have what we have done. What we do is we have a evolution equation and a constant equation. Constant equation are basically they are the conservation equation in a hypersurfaces. For each hypersurfaces, we solve this constant equation, and then this evolution equation takes over. So these are the these are along with this evolution equation and the constant equation. We remember that we also have to solve the GRHD equation, gravitational general relativistic hadronic equations, which are given by this. So once we can solve them simultaneously, we can have the evolution of the binary merger. Okay, so this is one of the binary mergers that we have performed. So here you see that two stars, first they are inspiring each other, and then once they touch each other, this is the maximum density, which after they touch each other, the maximum density rises, and ultimately you see that once the rotation slows down, they just blow up. That means they form a black hole. So I can play it once more to now analyze the gravitational wave. So this is the gravitational wave before the inspiral. Then there is this touchdown. Then this is inspiraling. It is not only rotating, but also it's like a top, right? It goes out and come up. So this is the goes in, come out. Okay, so this is the binary simulation that we have done. Now we want to do these binary simulations. These are the binary simulations where the two neutron stars were same, equal mass binaries. However, if I want to probe the twin, is that, remember, this is the twin, right? These are the twin stars. In the equation of state, what I am probing is one star which central densities lies here and one star where the central densities lies here. So if I merge the stars, two stars which are here, this will be their initial conditions. Okay. However, if I merge this star and this star, one will be this, another will be something else. This in there it says that it has some quark content inside, so their radius is completely different. And if I merge two stars from this part, we will have this. So you can see that depending on from where I am doing the simulations, my gravitational wave signal will change. Okay, so this is the gravitational wave signal from different. So this green is the AA part, this pink is the AB part, and this violet is the BB part. So we see that for the green AA part, it continues for a long time and then suddenly drops down. For this AB part, which is two different things mixing, it is completely different from that green part, and also this is different. And we can see this also, this imprint on the power spectral density, where you can see that different peaks are appearing at different frequencies. So these peaks are very important for astrophysicists and gravitational wave analysis, because this peak tells us this is the post-merger peak. This peak has not still been discovered till now. It will be probed with future gravitational detectors like Einstein telescope and all those things, cosmic explorer. However, you can see that even with this numerical simulation mergers, these peaks are different. And not only that, the ejected mass is also different. See, this ejected mass for this things is much larger than the ejected mass of the two different twin stars merging. And also, if I have the same twin, the ejected mass is very different. So this is one way of differentiating twins using binaries. So this I have showed you the twins of the category 2. Let us take another more extreme case is category 1, where so this difference in the radius is quite huge between the twins. So if I now merge this, so I am either exploring this part and one exploring this part. Let us say I am exploring this part, only taking these two stars and merging. So this is the case. However, if I merging one star of the mergers belongs to this part, and one part of the merger belongs to this star, we have a very different case. And then if I take two mergers from this, they are completely different. So if I now do this analysis, you can see that the peaks are completely different. These peaks are completely suppressed. Okay. So, and again, this dynamical ejected mass is completely different. So this is one of the way of differentiating twins. So twins. So to conclude is that twins are a special category of stars. This is a special category if we have a first order phase transition in our equation of state. So if we have a first order phase transition, the equation of state violates the universal relation. However, for those cases, you know that this violation depends on the density discontinuity. However, for twins, which is a special case of this first order phase transition, this violation depends not only on the density discontinuity, but at the point where this jump is happening. And another thing is, another way of differentiating the twins from normal first order phase transition neutron star or smooth neutron star is the binaries. So their power spectral densities are completely different, also their ejected mass. So twin stars are a way of observing or finding out new physics, if there is any, and whether twins really exist or not can be probed with this with the future gravitational wave analysis. So this is our group. Mostly this part has been done by this and this three people. Okay, so thank you, and thank you for your time.
Time for a few questions. Yeah, Sayantan.
So when you look at the mergers for the binaries, so what equation of state do you use? Because now the temperature will also rise, and then you cannot use this zero temperature equation.
No, these are not zero temperature equation of state. There is something called the adiabatic temperature which are inbuilt in this. So this equation of state takes care of the temperature rise. So this temperature of this mergers can rise up till about 80 to 100 MeVs. So that part is taken care of. These are not zero temperature.
And also when one goes to such a high temperature, there can be also phase transitions. It is not proven, but there could be first order phase transitions.
Yeah.
Also.
So this twins and all those things can probe those, because there is a line, right? That it can be a crossover, it can be a first order phase transition. I am talking about low densities, there is a first order phase transition. Because however, if the line continues till higher temperatures, there can again be a first order or a crossover. So this twin binary mergers can probe those using different equation of state, because you know that if I take a crossover or a first order, my equation of state will change. So this binary simulations can probe those part of the phase diagram.
And how will you detect it? For the tidal deformability will change, or?
No, for this thing. So this thing is that if I have a finite equation of the equation of state differs from here, you can see if my equation of state differs, there can be binary mergers. The masses can be very different. Not only masses, this merger depends on the temperature also. So this gravitational wave signature and this power spectral density will also change. So these are the things that we can look into to find out what are the changes in the equation of state that we can find.
Thanks.
Yes. Please.
Okay, so I have a question related to the slide Newton star equation of state. That slide.
At the beginning, right?
Yeah. Yeah, the previous to this. Yeah, this slide. So here in this bottom plot, this specific path of the equation state you are following by, I mean, constraining which conditions, like how you are getting this?
No, this is here, there is no constraint. Here only the randomizing of speed of sound. Now I can perform this million times. So I will fill this space, right? I can fill this space.
Yes.
Now I will put the astrophysical constant. What are the constant that I'm using is, so these are the constant. This is the gravitational wave merger constant. These are the two parts. This is the pulsar constant that I'm using, and these are the other three pulsar constant that I'm using. So these are the constant I am using from those to make my equation of state, to constant this equation of state. So it was previously it was filled whole here, right? So
Okay.
now I have with this constant, I have constant my equation of state to this boundary line.
So like based on those constants, like gravitational wave or Nizer, those things, so
Mhm.
that could follow any other equation of state path?
No, so once I have constant, then the only thing that remains is this part.
Okay,
Other thing has been rejected because they either doesn't follow any one of the constant that was given there.
okay. And your like four category of the twin star, some of the parts you are saying not stable.
Yeah.
So like based on what? dm by d rho c less than 0 or what?
Yeah, if you plot the mass as a central densities, if you perturb the star, what happens is if you perturb it, what happens that the gravitational wave, now you change the this gravitational pressure. What happens is now this perturbation, if you give a perturbation, this gravitational effect takes over and it collapses. The star is not stable one, it oscillates and then completely collapses to a black hole.
No, so I just wanted to check like radial stability, that thing has been studied, like stable against radial stability.
Yes,
Okay,
that
okay.
has been done.
Oh, thank you very much.
Thanks for the nice talk. I have a question which is probably not relevant, but let me still ask. So can we probe these phase transitions using continuous gravitational waves? I know that depends on the ellipticity. That's a major thing. But is there any effect here?
It can be probed by continuous gravitational wave. However, but that continuous gravitational wave probe has to be of a long time. It's not like only binary mergers we can do this, examine these binary mergers for a short time. But for continuous gravitational wave, you can probe the equation of state, but for that we need a long-term observation of that pulsars and all the gravitational waves that we are doing. It has to be a long-term effect. Here, binary mergers is a short. Even with a short gravitational wave observation, we can differentiate them. But for the continuous gauge, it has to be very long.
So there are no more questions.
Sorry.
When the collapse takes place, what decides at what radius it will go and settle? There are two radius which are available for you. Where do you find that information in the dust if you want?
Means
Where does it take place?
radius means this twins. Sorry.
You have same mass but different radius.
Exactly. However, as you have seen, if you are careful enough, let me go back in this binaries. Sorry, I'm taking a bit of time. So here, see, if your the central density is here, so the most stable thing is this one. If the central density is or the pressure of the central density is here, this stable thing is this. So depending on where your central density is, the stability of which star will depend on that. Okay.
Are there real examples in the collapse?
Yeah, because this simulations has been studied with gravitational wave 170817, right? These are very exact calculations.
Yeah, but these are all only simulations, but
yeah,
in
the
the
observation. So
the observations.
So for given the masses which were observed for GW 170817, this simulation will give you exactly the same results. Okay. There are also not only gravitational wave analysis, there are also means this multi-messenger observation was done for only GW 170817, but there are observations where only we have detected gravitational wave, and there are observations where we have only detected electromagnetic radiation like GRBs. Okay. So even with these simulations, we can predict those kilonova curves and all those things. Okay. So there are observations that we can predict it and check these simulations out.
Okay.
Thank you.
Right. To be remembered. The title is very interesting. Neutrino flavor and Anderson localization. Huh? Oh.
Oh, no, we are not. No, we are not muted. Okay, because then there is echo. Hi, can you hear us, Shudin?
Yeah, I can hear you.
Okay, good. Yeah, so you're, hi, welcome. So,
Hi.
hi, hope you are doing fine. So, maybe you can share your. Okay, so look, our next, Murthy.
Yeah.
So, introduce.
Hi, Sudhir.
Hi.
Welcome
Hi,
to
Murthy.
IMSC virtually.
Right. I'm
The,
sorry I couldn't be there today. Actually, I'm sorry, really sorry.
yeah.
Uh, I had a blood flu, so I couldn't come actually. Yeah.
Yeah. So you can start your
Right.
share,
I can share my screen, or how does it work actually? I cannot see.
people are telling me to tell you that there is some green arrow at the bottom. It's
1 second.
share
Yeah, I
screen.
can share. I can do the share.
Uh,
Right. I got it.
it's upward looking arrow.
Yeah. Uh, hello. Hello, everyone. Can you hear me? Yeah. I'm sorry I couldn't be there. I got a bad flu, and now I have to give the talk online. Actually, yeah. Right. Missing all of friends and everything. So I heard the conferences very well. I have been trying to follow it on YouTube, and I'm thanks to Manjari and all the organizers for giving me the opportunity to talk. Actually, today I'm going to talk about something which was supposed to appear a long time ago, but we got so engrossed in it that we kept exploring it a little bit more, and so on. So this is gone on using ideas of Anderson localization to explain neutrino masses. Okay, now BSM physics, as a landscape of a lot of beyond standard model physics, there are a lot of wonderful ideas and supersymmetry, extra dimensions, strings, composite. But sad to say that after the Higgs discovery, it has transformed itself to Berlin physics, actually. So you don't really see it. You don't have any signatures or anything. Okay. But it doesn't stop us to start speculating, or especially to look at if in all these models, is there a place to explain neutrino masses? Because we know the standard model is not complete. And especially, at least for the neutrino case, we need to explain the atmospheric and solar mixing angle, as well as their mass scales, essentially. The mass scales are extremely low compared to the electron mass scales, about 6 orders of magnitude. And they typically, it looks like that we are having mass scales which are exponential, like an exponential series, essentially. So we have 10 power minus 12 suppression compared to what is one second, I'll just make it full screen. Oh no, it's not. Yeah, right. Is it now full screen? Yeah. So there are a couple. The present work is again trying to explain these things with a couple of new ideas. It's a combination of two new ideas, sort of new in the sense they are about 5-6 years old actually. One is this is a pretty old thing in stringy landscapes. Essentially, that you can have randomness or disorder averaging or disorderedness in stringy frameworks, which means that essentially you can have couplings which are random in nature. You can also have it in masses. Essentially, you can also have in masses. So in terms of effective field theories, which derive from these things, quantum field theories, you can have randomness in your couplings. Essentially, you can have randomness in your couplings and randomness in your mass terms. There is a nicer version, field theory version of this by Dinas and Kumar, where instead of using strings or anything, you can have dark sectors with large symmetries. Essentially, the vacuum structure of the theory contains extremely large symmetries, such that the you can show that randomness is generated in terms of this large symmetries in the if you have a large symmetry, you can have a vacuum structure in which the mass terms and uh, uh, the couplings can take any values within a certain region, essentially. Now, so you have field theories which give you randomness, effective field theories are not okay. Effective field theories which have couplings and masses which are random. Now, there is also a simultaneous idea that you can use this uh, uh, randomness in couplings or in mass terms to generate exponential hierarchies in masses, essentially. It's a basic idea of Craig and Sutherland, which I'll explain to you. So here, look at this is the Craig and Sutherland model. Craig-Sutherland model, in which you have a bunch of fermions, which are in 4 dimensions, which are coupled with each other with the next neighbor. These are mass terms, essentially. I'll explain to you in a second. And vice versa. So both on the left, right, and right term. So you have mass terms which are like this, which are like nearest neighbor mass terms. So here is your kinetic action, and here is your mass matrix. This mass matrix has diagonal terms which are given by epsilon, and next to nearest neighbor mass terms, which are also TIs are dimensional full couplings. Epsilon I also are dimensional full couplings, which are masses, which are diagonal mass terms. Ti are, this is just to put it in Anderson language, essentially, just to put it in. TIs are next to nearest neighbor mass terms, which you can represent the full mass term as this particular thing. Now, what happens to this if you have a chain like this? Once you make them random completely, because coming from this fundamental theory in an effective theory, this is an effective theory. Once you have this thing, what happens is, in the limit, if you vary the epsilons, the diagonal mass terms between a range which is 0 to 8, all the wave functions of this particular Lagrangian are completely localized. So this is the sites. This can be nicely seen in this graph here, in which I have plotted on the x-axis the site number 1, 2, 3, 4, 5. This is for 8 sites. And W is equal to 3. These are in the units of TeV. And so when you randomly generate between, all the modes are completely localized. And so this is completely different compared to other models of extra dimensions or clockwork models or so on. So in which only the first mode, the 0th mode, is more localized. In this case, exactly like in Anderson localization in condensed matter, all the modes are completely localized. And the efficiency, so this makes it much more predictive compared to the other models, and you can compute these predictions. Now you can actually make it, you can actually look at how good is this localization, in the sense that is it so efficient? How much is the hierarchy you are going to generate it? So you can take, say, for example, only one chain, in the sense that you only take only left to right. Say, for example, there is a 0 mode in this case, or you can take left, right, and right, left, but don't really make these parameters random, but just make them universal, completely universal. In both the cases, you have localization only of the 0 mode. And the localization, you want to see how good is this localization of the 0 mode versus the modes of this Anderson localization. You can have a check. So you see, you can generate hierarchies of the order of 10 power minus 20 in the case of Anderson localization. It's extremely efficient. So this is so here I compared with with the 0 modes of the random clockwork mode, and then random site, meaning essentially epsilon I, which is random, and random coupling, which is also the T, which is the next to nearest coupling, which are random. And then if both of them are random, you see that you can really generate very large hierarchies. Now, in the standard model, we don't need such deep hierarchies, but we have something like 10 power minus 12 hierarchies, which are good enough for us to explain all the fermion masses and mixing angles. To begin with, I'll start with neutrino masses and everything, but a little bit more of exploration of the localization a little bit more. Now, on the left hand side here also, I just want to show you that how does things look like if I set all of them to be uniform. So the modes are completely delocalized. So you can plot them on the sides and they're completely delocalized. Whereas in the presence of disorder or randomness, they're completely localized, essentially completely localized on the right-hand side. Sorry. Now you can go further and say what happens if you have next to next and next to next mass terms in your model. Okay, so you can go further and further, and you can link all the possible in the chain, essentially all the possible fermions in the chain. You can fill up the entire mass matrix. In this case too, you have localization of only of the 0 mode, but the moment you turn all of them to be random, all of them get completely localized. This is the case I'm talking about, in which, suppose if I take 8 sites and make links to all the possible fermions, essentially. So the mass matrix will look somewhat like this. You have the diagonal mass matrix, the entire mass matrix is full, but we need something like a organization principle. So here we have taken the organization principle such that the coupling is changed by an order of B parameter as you keep going away from the diagonal. So if you move one step to the diagonal, you pick up a factor B. 2 steps to diagonal, you took a factor B square, and so on. So on, you fill up the entire mass matrix and then ask for localization of the modes. Yes, there is still localization of the complete modes essentially. So what we learned is that randomness, you can do the same thing with different geometries essentially. Other geometry which we realized essentially is something called a Peterson graph, which is not completely. So you can look at different geometries and corresponding mass matrices. So your mass matrix is represented by a very nice geometry. Okay. And so you have a graphical picture. So you have, again, in this case, you have part of them are next to nearest neighbor, and other part are not next to nearest neighbor. But then you have an organizing principle similar to the one which I showed you earlier. This is called a Peterson graph. So here you have all the diagonal terms which are completely epsilons, and the next to nearest neighbor terms which are completely described by this particular case. The Peterson graph is very interesting in the sense that, if you take all of them to be universal, if the mass matrix, all of them to be all same, all the epsilons to be same, all the G parameters to be same, all the B's to be same, you get half the modes localized on the left, half the modes localized on the right. Okay, so sort of half of the sites are really, so in between there is an intersection, sort of a lot of the modes are sort of things essentially. So along the left, essentially half the, you can see on the left hand side graph. But the moment you put in randomness in all these couplings, you have all the modes localized at whatever site we don't know. Now, if you want to do phenomenology with this phenomena, one of the important issues is how do you identify where it is localized? Essentially, you have no idea because of the randomness, inherent randomness into the picture. You don't know where the mode will be localized. So, which mode should be coupled to give you the right neutrino mass essentially? So, which mode? Where do you utilize? How do you utilize these exponential hierarchies which are being generated essentially in these couplings? Now, okay, I can, okay. So in the strong localization limit, in the sense that if the diagonal elements are very, very strong compared to the off-diagonal elements, it seems sort of you have universal features, which are for all. So let me talk about neutrino masses and mixing, which you can explain to all the flavors essentially. Are independent of the geometry of the chain. So you can think of the chain to be whatever chain it is. It can be Peterson graph. It can be completely non-local graph like this, or some other graph like this. Anything, whatever be the case, you have some universal features which are essentially saying that you can get neutrino masses. So, for example, the way you get neutrino masses for the Dirac case, you can do the same thing for Marano case also. Is you take the R1 mode at the left, you need at least the left mode. If you have two modes, the lightest mode on the R1 mode, and couple it with the standard model right-handed left-handed neutrino, and take the last mode, left-hand LN mode, and couple it with the right-handed neutrino essentially. So this gives you a sort of Dirac neutrino masses for the neutrinos, and the sum result is, so you need three such chains for the case of 3 neutrino masses. So the sum result is that you have you can explain neutrino masses of the order of eV in this case, but the mixing angles are completely anarchical. So the resultant mixing angle, the randomness nature also follows through this particular case, and the mixing angles are completely anarchical. So you have a prediction. So this is independent of the geometry. You can take any geometry you want, a Peterson graph or whatever graph you want to take, and write a corresponding mass matrix for it, and then get neutrino masses like in the case I had written. You can do the same thing with Marana masses. In the Marana masses, it's much harder to get neutrino mixing angles. But you can do much more. This is the same. This is for the Marana masses. You have Lagrangian in this particular fashion. You add a Marana mass term here, essentially. I'll come to the if I have time for the Marana masses. To summarize, the strong localization limit has a prediction that you have anarchical mixing angles for neutrinos, which sort of, I don't think it really fits the data very well, but it's a prediction of the theory essentially. But it doesn't mean that we had to rule it out. No, the actual thing is we can inverse it. We can take the limit of the weak localization or the weak disorder limit. In this case, what happens is you don't have a complete localization of the wave functions. You don't have complete localization of wave functions, but you can have wave mixing angles which are localized. So you don't really need wave functions. You don't really have wave function localization, and like an Anderson-like effect essentially. But you can nicely generate localized mixing angles which fit the data very well actually. So here you see theta 1, 2, theta 2, 3, and theta 1, 3 fitting the data very well, and the masses also pretty well. The weak disorder limit is an example where you can show it essentially. And this, you can show it in, this works very well for the first case, the Anderson, the nearest neighbor only. It works very well. The variance is extremely small, but the moment you start plugging in the extra terms, essentially, if you are starting seeing the other nodes also beyond your the diagonal terms, you start, the variance starts increasing, but you can still fit it. But of course, there is no real localization of the mixing angles in real sense. Okay. For the Marana case also, you can get, yeah.
You have 10 minutes.
Yeah. Okay. I was hurrying up because I thought I had less time actually. So sorry. Yeah. For a Marana case also, in the Marana case, okay, I can explain the Marana case a little bit. So here you have the kinetic term, and then again add the same Dirac like action term, but you break the electron number by a mass term of this particular type, the W essentially. W is the same W which appears in the randomness essentially. The scale of the localization, the scale of the randomness also will break the mass of the also is the scale of the randomness of the scale of the Marana mass scale. Now in this case also, but in the weak disorder limit, that means epsilon are less than or equal to the off-diagonal terms, or all the mass matrix elements are roughly close to each other essentially. You can localize the mixing angles. You don't localize the wave functions. You don't localize the wave functions, but you localize the mixing angles. Here too, the reverse is case compared to the Dirac case. The variance is larger for the local case compared to the Dirac case. Now there is a couple of caveats which you should remember. One thing is that one of the conditions is that if you really go for there are some free parameters in the way neutrino masses are generated, essentially. So these are considered to be order 1. So for example, these Yukawa couplings are taken to be order 1. Now, if I insist, if these Yukawa couplings are also completely random, then even in the weak disorder limit, I don't get localization of the mixing angles. So in principle, I'll only get anarchical mixing angles because essentially I'm setting them to be completely random. That it essentially becomes it's understandable because it's like taking an anarchical mixing matrix, anarchical mass matrix, and so on. So you take them to be order 1, essentially some order 1, and so you get nice localization of the mixing angles. Now you can generate, while you can explain the neutrino masses and mixing angles very well, you can easily explain the charge lepton mass matrix as well as the hadronic sector. Okay. I'm not going to share any results from the hadronic sector because I'm focusing on neutrino masses, right? Neutrino flavor. Now, phenomenology. And one of the important things is phenomenologically, is this model viable? As I said, this model is extremely predictive in the sense that all your modes are fixed, their masses are fixed, and you know what is your lightest mode, and you know what it is, essentially its couplings are, and so on. So we calculated, say, one of the easiest things, first things to do is calculate radiative decays of muons, essentially, which is or leptons, charged leptons. So we computed the limits coming from mu going to e gamma, which are the strongest ones, essentially. And we show that this is within this thing. A large part of the region of the parameter space is already, this is a heavy model. This is the model, it sits at TeV scale. A large part of the model is already being probed by mu going to e gamma, essentially. So the constraints become weaker for partially local and non-local cases. So, so this is interesting in the sense that if you take completely non-local model, like means the mixing comes dominantly coming from some non-local interaction, non-local mass from very far away master, the mixing is weak by the time it comes here. So it couples to the leptons and the W very, very small. And so the mu going to E gamma is also very weak, essentially. The mu going to E gamma and the collider signatures are also very weak. So I stop here, essentially, that so the outlook is randomness in coupling can lead to exponentially hierarchical couplings. In the regime of strong coupling, the geometry of the mass chains does not matter significantly. They predict hierarchical neutrino masses and anarchical mixing angles for both Dirac and Majorana scenarios. In the weak coupling regime, the geometry does play a role and can be chosen carefully to localize the mixing angles. And we also looked at rare decays and collider signatures for all geometries, essentially, for strong coupled systems, essentially, and they become weaker for non-local and partially non-local cases compared to the local case. Okay, that's all I have to say. Thank you.
Thank you. Any questions here?
Hi, thanks for the nice talk. So my question is, how stable is this localization if you add, let's say, one loop corrections?
Pardon?
If you add quantum corrections, let's say at one loop, how stable is this localization remains? Is it still localized or something changes? What happens?
Quantum corrections. Now the question is, these are effective field theories. Okay, so you have to think in terms of effective field theories. Now, if you because averaging over disorders essentially, or averaging over all the randomness in the couplings. Okay. Now, if you want to still compute, you can compute. It depends on the model to model essentially. If you think in terms of purely clockwork like scenario, you know that radiative corrections can become very important in the clockwork scenario essentially. Like okay, in this case, we computed the radiative corrections. Say for example, mu going to E gamma or something essentially. We computed corrections to the Higgs because so you average out all the, you fix all the number of modes. You fix the localization may not be. Okay, I understand your question. The localization is not stable because the localization itself is changing with the random number. Okay, if you change within that range, okay, it is localized. As long as your epsilon and t's are there, all the modes are localized. Now, which mode is localized where there is a randomness essentially? That's only randomness. The localization itself is sort of fair.
Thanks.
Harry? Hi, Sudesh.
Yeah,
I got confused with your notation. You had L and R and also a psi. Would you mind clarifying? So L and R are the two neighboring sites, I suppose, the fermion.
LR and R, okay, I can
And
share.
then you also had the psi, and those live at the site or what?
Okay. So
I guess
L and R,
see
okay, I can
what
just
is the
show.
role? What is the role of psi?
No, psi I introduced only. Psi is L and R as long as we are talking about Dirac cases.
I see.
Okay. For the Marona case, I introduced a new fermion. Sorry. I'm
So if
going
you
up.
can show in the Dirac case, maybe that will be helpful.
Right. In the Dirac case, there is no psi.
Ah, I see. Okay.
Okay. In the Marana case, there is a psi, which is a new fermion I introduced. Okay. It's just to break the lepton numbers.
And that doesn't get an I index. It's just one single field or what?
You can, this is for one generation.
Okay. So there is a single fermion which
Right.
couples to L.
Right.
Okay. all
Yeah,
right.
L1.
And what is its role? Why do you have
No,
that?
no, you want to, its role is essentially to, this
So
is
that,
exactly like seesaw.
okay. Yeah, got it.
There's nothing else.
Okay. It breaks the lepton number
Lepton
and
number and just, this is seesaw. This is
Okay.
Dirac.
all right.
It's like right-handed neutral.
Okay. Sorry, can I ask one more question? Yes. Okay, so the localization itself, I guess it is obvious, but I don't see it. If you have a very strongly localized, you have a very suppressed mass. Is that
Exactly.
okay? And is it
That is
why is
purely because,
right.
no, if you have a very strongly localized, the hierarchy generated is very large. It can be, okay, if it is very strongly localized. So you can think in terms of the wave functions. The wave functions
Right.
are very strongly localized. So you're coupling to the tail end of the wave function and it's
So I couple to which one? To the Higgs, is it?
Depends again. Yes, you couple to the Higgs.
And so its coupling to the Higgs would be very suppressed because that lives only
Yeah,
on
because you're
something.
imagine exactly like extra dimension.
Okay. That Higgs
Okay.
lives only on an
So Higgs can live in. So the left wave function, you put it on the right hand on the one brain. The right wave function, you put it on the another brain.
Okay.
And you can put the Higgs anywhere you want in the bulk or whatever it is.
Okay.
And that gives you a very small suppression because the wave function overlap is very, very small.
Okay. All right. Thank you.
Yeah.
Any other question? Yes.
Hi, I just wanted to understand, do you decide in advance which site you want to couple the Higgs to? Because you said that the localization can change, so like unless it's going to be suppressed, like if you decide in advance, I'm coupling to the, let's say, 10th site, And then is
Right.
it
So,
robust that
so
it's always?
once your number of sites are fixed, okay. So there are two ways. Either you fix, you can put it in any site you want. You can do it at any site. This thing works.
Okay.
This thing works.
You're saying you don't know where it
So
will.
as long as you
It's
put,
localized on the.
yeah. As long as you put one wave function on the left and one wave function on the right.
I
Yeah.
see.
Yes.
Hindu.
No, so I just to continue that question. So how do you know that that object is actually a neutrino which is very light, because your masses are also random, right?
No. I identify my left-handed neutrino. Okay, my masses are random in the sense my masses are random. It's true, but once they are localized, the couplings are fixed, and the couplings to the Higgs give you the neutrino masses. Okay, once the fields are localized, I know what their couplings are. So the couplings you can demonstrate with respect to the localization length. Okay, so if you know the localization length, I don't know when I must have written it somewhere essentially. So the localization length gives you what is the coupling which gives you the thing essentially. So
Oh, that's why you want it to be at the two endpoints, is it?
yeah, exactly at two endpoints.
Oh, I see. Okay. I see. Okay, thanks.
Any other? Yeah, Sand.
Hi, Sudhir, if there are sometimes it happens that in an Anderson localization, the localization of the modes depend on how many sites you have in the system. So,
Right. The
so
lowest number of modes we were able to have localization, meaning efficient in the sense we were looking at localization of the length of say 10 power minus 6. Okay? A hierarchy of 10 power minus 6. We were able to get it with 8 number of sites.
Okay. Okay, thanks.
And if you, of course, if you increase, you can get, like I said, if you can play with, and you can really get very large. Yeah. For the number of modes, n is equal to 8 is calculable, so we can do it very easily.
Yeah. Okay, thanks.
So let us thank Sudhir. Go to the next talk by T. Manoharan. We'll be talking about holographic dark energy, possibility of negative dark energy at Z greater than or equal to 2.
Okay, so I'm audible, right? So good afternoon, everyone. Thank you very much for having me here and giving me this opportunity to come here and talk about negative dark energy, which is kind of a speculative title to have. And what is holographic dark energy is going to be my first slide. So dark energy, as you know, it's kind of like an exotic fluid which people introduce in order to explain the late time acceleration of the universe. But what we need is something as simple as a cosmological constant to explain that. But with cosmological constant, we have so many problems associated with it, such as the coincidence problem, fine-tuning problem, etc. And even if you take the concordance lambda CDM model, it also comes with several kinds of tension, such as the Hubble tension, SA tension, and so on. So the question is, can we solve it with the dynamical dark energy? Has always been an option. So holographic dark energy density is a proposal which goes like this, where we have a dark energy density, and this MT square takes care of the units and everything, and L here is the IR cutoff. So this was proposed in a sense where if you want to do a quantum field theory calculation, and a general relativist would not come and argue that you are doing something wrong. So this comes from something called as a CKN bound, popularly known as the Cohen, Kaplan, and Nelson bound. And although the exact origin of holographic dark energy can be a little speculative, and we can argue against it, but it kinds of work. So let us see why it works and how it works, and what are the perks that we get from it. So we start with the standard Friedman metric, Friedman-Lemaitre-Robertson-Walker metric, and obviously we have the Friedman equation. So we are not going to consider any kind of modification to the gravity theory, although we can, in principle, we can translate all of what I'm doing into an FOFR theory. But nevertheless, we plug back this dark energy density to the Friedman equations and try to solve it. So we are not considering any sort of exotic interaction between the energy density that we have, like we are not considering dark matter interacting with dark energy or any other sort of interactions are being considered. We are kind of using the standard Einstein gravity picture. Then the question is, what is the IR cutoff we are interested in? So there are several IR cutoffs, and the popular one is always the Hubble radius, and you can modify that with the apparent horizon if you are working with a non-flat universe. But then again came the question of causality. There is also options for particle horizon, future event horizon. All these can be a possible cutoff, which can be included in the dark energy density definition. But then again, due to the consideration of causality and several other factors, Granda and Oliveros came up with this IR cutoff, which I'm going to call as LGO, which has the Hubble parameter and its derivative in the picture. And alpha and beta are taken as constant, but although that can have a dependency on the redshift, but that will be a much more general case. And then we define the Granda-Oliveros holographic dark energy, and we substitute back into the Hubble parameter. Then we have a differential equation of this form, which upon solving it, we can solve it analytically, and we can get a definition for the Hubble flow. But the interesting factor is that in principle, at least when you look at this particular expression, equation number 9, you can see that you can almost rewrite this in terms of a WCDM model. But if you were to do that, or in the case that we are going to discuss right now, we see that the dark energy is kind of intertwined with radiation as well as matter. And if you are interested in non-flat universe, you can also have the curvature part also there. But there are special cases. For example, if you take beta to be 2/3 times alpha, then interestingly, the matter term decouples from the definition of the dark energy. And if you take beta to be alpha/2, then the radiation terms decouples, and so on. So what is the value of alpha and beta is obviously the question. And for that, we need to constrain this model using the observational data. That is the typical way how cosmologists work. So for that, we define the dark energy density. For time being, we are not interested in any sort of interaction, although we can do that. But nevertheless, we define the dark energy density by removing whatever matter and radiation components here. We take that out, and what we are left with is the density parameter for the holographic Granda-Oliveros holographic dark energy density. And the equational state is something that we define like this. But for consistency or for easy communication, we can rewrite, instead of alpha and beta, we can have WZ0 and beta as our free parameters, the additional free parameter. And WZ0 is the present value of the dark energy equational state, so that we can easily translate what we are getting here to other literatures. Because if you look at the Daisy result recently, the dark energy equational state at the present value is slightly greater than that of -1, which is indicating a quintessential behavior. If it is less than -1, it is kind of behaving like a phantom behavior. But interestingly, there are models in which they can be transitioned from quintessence to phantom or phantom to quintessence, called as quinton models. And we'll see what this particular model is telling us. So in order to do that, we take several data sets, obviously. So this is a combination, D4 is a combination of data sets such as the OHD data, which stands for observational Hubble data, the BAO data, the CMB shift parameter, the QSO data. So we are calling it as the D4 data set. And when we do the chi-square analysis, which is chi-square minimization, we have the Hubble parameter, we have the data points, we can fit it and do the chi-square minimization using the standard MCMC tools. And we can see which model is performing better. That is one, at least a quick check in order to understand whether the model is consistent or not. And we can see that almost all the models are pretty much close, although WGO-HD model, which is our model, is slightly favored. And let me tell you why there is two GeoHD model here. If you take the present equation of state, present dark energy equation of state to be -1, that is what I'm calling as GeoHD. And if you put that WZ0 as a free parameter, we are calling it as a WGeoHD model. And then we can include the Pantheon data, which is the supernova data, without considering the shoes prior. We can still see that these models are obviously kind of giving similar results. But when we include the Pantheon plus, including the shoes prior, you can see that the model tends to be highly differentiated within the chi-square itself before going to other statistical parameters which can differentiate the model. So we can see that the WGHD model is slightly favored by the Pantheon plus with the shoes prior data. So obviously the best fit values has to be discussed. So for various combinations of data sets, we can have the matter density, which is consistent with the concordance value 0.3. So I'm writing in terms of 10 to the power -3, that is why it is roughly closer to 300. Then the Hubble parameter, obviously the Hubble tension is not being solved. Whenever I use the shoes prior, I'm getting a higher value of the Hubble parameter. But whenever I'm not using the shoes prior, I'm getting something closer to the TRGB value or the Planck value. But what is very interesting is the value of beta. So the value of beta comes closer to 0.66, which is very close to 2/3. So in the very beginning, I said that when a beta is very close to 2/3 times alpha, we are essentially decoupling matter from the whole picture. And if you take the very first equation and let us say that, okay, radiation is not so dominant in the late phase, we can remove that and we can assume the universe to be flat. This model turns out to be exactly equal to the lambda CDM model. So that is interesting to observe that the value of the beta is very close to 2/3, although it is slightly different. And there is another interesting factor that comes around. This Z dagger is not the transition from the deceleration to acceleration. This is where the dark energy gets from negative value to a positive value. So in order to make that more evident, if the dark energy density is having a transition from negative value to a positive value, which means the equation of state will be having a pole in it, or a singular point will be there. And that comes with extra consequences. So let us see. And another important feature to look here is that whenever the Hubble parameter is slightly higher, that means if we were to claim to have solved the Hubble tension in some way, the redshift transition should be close to 2 or slightly above 2. And I'll tell you why it is. I'm quoting the value 2 of more and over again. So let us see the confidence intervals for the free parameters. So we can see that the best fit value for most of the data combination, except for the shoes prior, the beta value close to 2/3 stays within the confidence limit. And the WZ0 value, the present value of dark energy equation of state, comes close to whatever is taken as the standard values in the literature. And we can see that it is mostly lying in the quintessence region, which means the quintessence is preferred. Which also means one can also say that this is supported by the recent DC result, which also prefers a quintessence kind of behavior for the dark energy, although it might have been phantom in the past, but at least in the present, it kind of behaves like quintessence. So this is the confidence contour for these analysis. And I should mention that during this analysis, okay, when we are trying to include the Pantheon data, you have to do an integration in order to fit the model. But when you're doing the integration, it takes up too much time. But then I have to mention that the hypergeometric function, which we discussed in the early morning session, came to the rescue, because that fastens the whole process by 10 times faster. So that is one thing that I wanted to share. So we can have the confidence contour for the other free parameters. And we can also see that the most of the results are slightly inclined towards the Planck values. So we are not essentially solving the Hubble tension, but there is an interesting things that need to be mentioned. But before going to that, let us see other features of the model, which is to validate the model using other statistical parameters like AIC, BIC, and Bayesian inference. And we can see that in most cases, the lambda CDM is taking the golden stand, and there is the other models are not performing over the lambda CDM model as it was shown in the chi-square analysis, because there is extra parameters coming into the picture. So we need to penalize the model for those extra parameters, and these quantifiers does that. But we can see that whenever you are using the Pantheon Plus data, the WGOHT model is slightly favored, although it is not a strong evidence, but it is something that we cannot rule out. Nevertheless, the interesting facts comes with the dark energy equation of state. So this is an analytical expression that you can derive from the previous expression shown, but let us see the graphs. So what we can see is that so anything that goes beyond 0 is kind of like the future, and 0 is the present, and this is the past direction. So we can see that the dark energy equation of state kind of starts from 1/3 and then falls to 0 and then falls to -1. So this is kind of like a tracker scalar field. What I mean by that, we know that during this particular redshift, that is of the 1 plus redshift goes over like 1000, that is the, if you are going into the path, that is radiation domination. So during the radiation domination, the dark energy kind of behaves like radiation itself, because the equation of state parameter has a value of 1/3 and then goes to the value close to 0, which means the dark energy is kind of mimicking whatever is inside the bulk. Hence, it kind of captures the true essence of holographic dark energy models. And this is an interesting feature which shows that during somewhere in the past, there has to be a transition from negative to positive dark energy. That is why we have a singular point in the dark energy equation of state, because log of 0 is kind of making that singularity there. So does this solve anything? Well, it turns out that there, along with the Hubble tension, which is the popular one, there is some sort of anomaly with the BAO alignment alpha observations. So BAO alignment alpha, so BAO, we are very familiar with the baryon acoustic oscillations. So there are two ways of doing that: observing the alignment alpha forest and also the galaxy clustering. So here I'm using the Pantheon Plus along with the Schuster, and we can see that the W CDM and the lambda CDM tends to have some sort of mild tension with the BAO alignment alpha observations. But the GHD model doesn't. So that is an interesting observation. Even if you are not using the shoes prior, that still stands. So one of the interesting features that is been reported recently, including the sign switching lambda CDM model. So we were a transition from negative cosmological constant to a positive cosmological constant happened somewhere between the redshift 2 has been reported widely. And then there are other model where people are considering modified gravity theory, like Hordensky gravity and so on. They all show these kinds of features. Although this random holographic dark energy may not be the final answer for everything, although we can still find ways to say that, okay, this construction might be, may not be the most appropriate one. But nevertheless, the fact that it kind of relaxes this tension, or the tension that happens somewhere around the redshift 2 and above, has been addressed recently in several other literature, with the common feature that the dark energy being negative. So with that, I conclude this presentation. Thank you.
Hubble tension does not bother you?
In fact, when we try to use the CMP Planck prior for the distance scales, we can in principle solve the Hubble tension. It does gives a Hubble parameter of the value of 73, but I'm not reporting that because the present value of dark energy equation of state goes to phantom behavior. So such features are still there. So we can essentially solve Hubble tension using these kinds of models.
Okay. Shaji was our student.
So when I applied for this conference, I was wondering, is there any connection with me to IMSC? So it turns out that Dr. Shaji,
I taught him.
yes, yes,
He worked with him. They collaborated. He was my first batch of students.
Yes. He used to tell so many stories about IMSC, and that is one reason for me to apply.
He's a good storyteller too.
Yes, he still is.
Yeah, nice. Nice to see Shajis. Yeah, the next speaker is Tausik. Oh, thank you. Huh? Yeah. We'll be talking about prospects of dynamic radius jet clustering algorithm. And there, let's see.
Hello. I think I'm audible. Okay. So, okay. Yeah, let me first thank the organizers to give me this opportunity to talk about my work that I'm doing on jets for last few years. And this particular work is a method which we developed with Vishwarup Mukhopadhyay and Ritesh Singh when I was at IISER Kolkata. So that is the name is dynamic radius jet clustering algorithm. So that I'll be talking about today. Okay. Okay, so the date is wrong anyway. So let me first motivate you that as we already know that the high energy colliders are actually very, very crucial in advancing our knowledge of particle physics that we are seeing for a decade, more than a decade now. And one of the central object is basically jet, which usually appears from high energetic quark or gluon, which are basically colored particle. So those are so the jets are a central object in any high energy collider. Okay. So now, as in the morning session, Songshoptak already pointed out that so not only quark and gluons can produce jet, it is like boosted heavy particles can also produce jets if they are their energy is very, very high, and then those jets are slightly different from characteristics are slightly different from the QCD jets, and they are called fat jets. And now, so nowadays, any BSM or SM studies actually focuses on these objects, jets, and fat jets, and try to extract some things from it. Okay. And now I will like describe this thing. So current days algorithm that we use are basically KT, anti-KT, and CI algorithm, which are called fixed radius sequential recombination algorithm, jet algorithm that we use. They are good algorithms, but they have some deficiencies like inadequate that we wanted to like go further and solve. Okay, so that method is like variable radius, which is like slightly different from the fixed radius algorithm that we implemented, and I am trying to motivate you and show you that that is useful. Okay. So let me give you very, very brief and quick introduction to JET. JET is basically collection of a bunches collimated hadrons. For example, let's say if a quark or gluon, which is a colored particle, is energetic enough, then it tends to shower, and after the shower they hadronize, and then those hadrons are extremely collimated, and those hadrons are detected at the detector, but they're very, very collimated, and those collimated hadrons, the collection of those collimated hadrons, we usually capture and call jet. Okay, so that is the appearance of the QCD jet. We say they tend to be like light and narrower in size. But then again, in the high energy colliders, which is like, for example, at the LHC or any future colliders, what happens that heavy particle can also be produced at a very high boost. Okay, so for example, W boson, Z boson, or top or Higgs boson. For example, so Songshoptak talked about W boson, which can produce a fat jet if that produced W boson is actually very, very boosted. Okay, so that has been shown here. Let's say, for example, top quark actually decays. It has three body decays. Let's say bottom and W subsequently decays to two quarks, a quark and anti-quark pair. And in a sufficiently boosted region, it can actually decay. These three decay products come within a very small cone, and the showering from these quarks again produce a jet. But the characteristically, this jet, for example, W jet and W jet, Z jet, or top quark jet, versus these quark and gluon jets are slightly different, because this tend to be narrower in size, and mass tends to be very small, whereas top quark and these are slightly fatter in size, and their masses are heavy. But in any case, we have to cluster these highly collimated bunches of hadrons from the detector, and we need to get the jets. And for that, what we use are called jet clustering algorithm, or sometimes we call jet algorithms. So be it a narrow jet or a QCD jet, so we need an algorithm, and that algorithm is called jet clustering algorithm. Okay, so for example, this is one. This is let's say it is an iterative method basically. So you put the list of whole 4 momenta from an event, 4 momenta of the hadrons that you detected, and you put it in the list, and you go through this procedure, and you'll get the jets. Where we have to define basically 2 distance parameters, and based on that distance parameters, we have to optimize and iterate over the things. And so popularly, there are like 3 different algorithms that we use: are Cambridge-Arkin, KT, and anti-KT algorithm. And importantly, from this, what I want to show, there is a parameter to this theory, apart from an integer parameter that is there as p, this R0 parameter, which typically sets the radius of the jet. Okay, so this is this particular method, we call it fixed radius algorithm, where the typical size of the jet is fixed by the radius R0. Okay. So now, as I mentioned that in the QCD case, this is tend to be smaller the size, whereas in the fat jet case, it tends to be bigger in size. But if we give only one parameter, then we will not be effectively capturing the 2 different sizes in a single go. Okay, so that's where we actually propose that if we can modify this R0 to kind of a dynamic quantity by modifying it to R0 plus sigma I, where sigma I is defined as the basically standard deviation of delta R, the distances of the constituents of a jet when the jet is getting formed. Okay, so if we do that, we can show that it can be useful. So in our case, so earlier it was like CA, Cambridge-Arkin, KT, and anti-KT algorithm. So in our case, we call it dynamic radius jet algorithm, and that's why we like for the same thing, same p values, we just give name drCA, drKT, and drAK. So those will be for future reference. So now our question was like, why this? So now one might ask why this particular variable is useful. So there are 2 reasons that we found useful, that why this is useful. One is like this sigma I is basically the standard deviation of the delta R's between the constituents of a jet. And that is basically the fuzziness of a jet. And since the fat jets, the jets coming from the heavier objects, tend to be fuzzier, so that's why this works. That was one of the explanation. Other explanation is that there are substructure observables which are useful in discriminating from normal QCD jet, from the top jet and W jet. So if you see this energy correlation function, which is defined the same way as we defined earlier in this sigma I definition, slightly different from it, and you see that this tends to be higher for the top jet, tends to be a little lower for the W jet, and for the QCD jet it tends to be smaller. So this is actually from an observation from the atlas. So this already tells that if you use that parameter, it could be useful in dynamicizing the radius of the jet. Okay. Having said that, let me show some of the examples where we could see potential use of our method or of our development. So this has been implemented as a plugin to already existing framework by which we cluster the jet. It's fast jet
the third version of it, and the implementation is available in GitHub. And then we potentially used it in two different types of events. One is in a proton-proton collision at 13 TeV. In the top, and the final state is top and jet. Why did he choose this top and jet? Top will give us fat jet, and whereas J, which is basically quark or gluon, will give us narrow or QCD jet. So whether we wanted to see that whether we can get two different size objects from a single event. And another example, which is not within the standard model, where we incorporated some sequential model where bottom partner has been called, and then this bottom partners actually decays to heavy bottom partners decays to top and W boson, and where we can see the utility of our model. And this has been implemented in model building, and then event generation has been done in MatGraph and Pythia. Those are technical. And let me illustrate one particular event. So basically, the event here is in the eta and phi plane, where these dots are the hadrons, and the sizes of the dot represents the energy or PT of those hadrons. Okay, so now from the simulation, what we can see that these three big dot dot collections are basically three prongs of the top quark, and this is the quark or the gluon. Okay, and now so both represent the same event, exactly the same event, but one is clustered with standard antiquity with 0.5 radius, whereas the right side has been clustered with the dynamic radius with antiquity, and the starting radius R0 is 0.5. Now what we can see is that this particular jet, which is QCD jet, which tends to be smaller, that has been captured by antiquity algorithm, standard antiquity algorithm, and also our algorithm correctly. Whereas this particular these three prongs could not be captured by the antiquity algorithm. It has been captured as two different jets, whereas our algorithm could capture the whole decays of the top quark. Okay, so that's the thing that we could achieve with this algorithm. So this is for a particular event, and maybe for the best event that we could see within our sample. Now, but we wanted to see that whether this is gaining at least statistically something. So for that we defined. So before that, let me tell that this is a jet mass distribution. Okay, for two different cases. So the shaded ones are for the standard antiquity, and the lines ones are for our algorithm. And here what we can see that for the QCD jet, so this is the green, these are represented by the green. So the mass for both the cases are actually similar. The distributions are similar. And another thing that we achieve is that this acceptance. How do we define this? This number of top we could reconstruct with a particular algorithm divided by total number of events that we produced. Okay, so for standard antiquity algorithm with 0.5 radius, we see that we could capture only 14% of the events that we generated, whereas with our algorithm we could actually capture roughly 49% or 50% events. So that is a big improvement that we can show. Okay. And on the right side, what we plot is the final radius that we get with our dynamic radius algorithm. So here also we can see that starting from 0.5, the QCD jet, which is represented by the green curve, here its final radius is not large enough. It can grow and the max up to 0.6 or something, whereas for the top quark it could grow up to 0.75 or 8. Okay, so that's the achievement we get. And then we try to see that what would be the this acceptance variable that we defined with respect to let's say the radius if we choose. Okay, so this is for dynamic radius that is our method, and for the anti-KT we can see that almost everywhere we get higher acceptance for our algorithm, whereas for the anti-KT it's lower. Okay, so now so this increases, and then it sharply drops. This drop is not because that it is performing poorly. It is performing poorly because it is now started to capturing a lot more things which are essentially garbage. So there should be some optimal choice for this, and that we can see. Okay, so these three are for three different algorithm: anti-KT, Cambridge and the KT algorithm. Okay, so this is for first illustration, and then the illustration from a different theory where we have two tops and two W. Here also we can see on the left it is for anti-KT with 0.5 radius, and the top could not be captured here the whole thing, whereas in this on the right side we can see that we could capture both the tops very effectively with this algorithm. And again we can see that we get fourfold or like 3.5-fold gain in the acceptance. Okay, so that is the thing. And then let me come to the summary that variable radius jet algorithms are actually useful in certain cases in search for BSM or SM. And we actually developed an algorithm which is called dynamic radius jet clustering algorithm, and we discussed the idea, implementation, and utility of it. And it has application in the case of like heavy object studies and other things. And in the outlook, what we are now doing are like we are seeing the potential use of this application and trying to figure out how this can be useful in quark-gluon discrimination case, or some event topology case, or finding the dark jets. And then the sum of the studies that we are doing with CMS or Atlas Open Data to try to see its like sensitivity towards the pile-up effect and jet energy calibrations and other things. So that we are doing. And thank you everyone for listening. Hi.
Okay, so very important question. Is there any scale dependence in R naught? I mean, because clearly as a function of root S, I would assume the jet sizes will change, right?
It typically does, but we have some standard choices for the anti-KT, right? So, for example, if you want to capture the QCD jet in the anti-KT, we take it to be like 0.4.
No, that I understand. But since you're doing this acceptance studies, right now you've used the 13 TeV data, right? So if you use some other data, I mean, it might be that your
optimal choice can be different.
Can be different. Okay. But right now your code actually can use arbitrary values, right? Or
yes. You start with some radius. So R naught is the starting radius, initial radius, and then it adopts its sizes accordingly.
Okay.
As it.
Nice. Thank you.
Sorry. ZPT distribution. Or, no, sorry.
This radius, it will depend on the ZPT, individual ZPT.
Yes.
So overall scale of the event does not matter so much. If the PT is large, then of course it will be will depend, but individually we are looking at individual jets. So that's very small. That is very small. 13 to 36 to 13 TeV. The cross section is not much log dependence. I think individual ZPT will matter most, but maybe we can discuss.
Yeah. So basically, we have to like for set of events, we have to choose a particular R naught, right? It's not that event by event we change it. I mean,
again, I would say that depending on the ZPT, it will be.
Yes.
If the ZPT is 40 GV, you will choose a standard R naught.
Right.
If it is 400 GV, then you have to worry.
So this particular algorithm for our case, at least, we are interested in the boosted object. So basically we are above like 200 or 300 G, above 200 or 300 G. Right. So in those cases, typical choices that we found are like 0.4, 0.5 are good choices. In some cases it can go even up to 0.6 or 0.7. That are not.
How large can make your algorithm vary? Because at some point there will be hybridizations. To be large. How do you accommodate in your dynamical radiation of
No, R naught cannot actually, the way we implement it, it can always increase. It's not R naught increases, but it starts from some R naught and the radius adapts and it always increases. Okay. And how big, if you ask, then I would say it's not a, yes. Then what will happen, that then the pileup will start come in, and then your mass distribution, other things will get screwed. So for our case, we see that for this case, it is 0.5 is good enough. And then if you go 0.6, 0.7 in some cases, but not beyond that, it will be difficult.
So this algorithm, the examples that you showed, there was what you knew to be a fat jet, which was being wrongly interpreted as two overlapping jets by
Right.
that decade, right? But the opposite can also sometimes happen, that there are actually two very closely spaced jets. Would your algorithm manage to?
No, this algorithm cannot do it. In those cases, what we usually do is like we take the whole jet and then we find the subjet inside it. And then you can do whatever you want to do.
So you have some algorithm,
right?
Identify jets. You showed us examples where the existing algorithm is disidentifying a fat jet as two separate overlapping jets.
Right.
But equally, likely, I guess, would be the situation where there are in fact two overlapping jets.
Right.
You misidentify, or you have something in your algorithm that understands that no, I have to actually further subdivide.
No, in this algorithm, we don't have that. We don't have it. That's actually a very difficult question, even.
Then, isn't it a bit of a worry that you will start identifying lots of things as fat jets, but they are in fact not fat jets?
Yes, that is actually a worry. That is why.
Fail acceptance ratio, so you've given the correct, like, so the good acceptance ratio.
Yeah, that I understand.
The bad acceptance ratio. Yeah, so true positives, false positives, something you give some name, but this is, I would say, an important check.
Yeah, this is an important check. So basically, so these algorithms, if you see, those are like it takes care of some statistical things. Okay, so now what you have to do is you have to take that jet as jet, and then you have to do substructure analysis on that, and then you can throw away some of those unwanted events. Yes. So those are the usual technique. But during the clustering of the jet, you dynamically throw away certain events based on your criteria. Could be done, I think, but has not been studied very well, actually.
Okay, but maybe just one comment to Vasudhan. So you need to measure the true negative surely, but then you have to specify the signal you are looking for. That by putting this algorithm, what is your true negative? Let's say triple Higgs. I'll talk each Higgs going to two BZs. So the event is very busy. Or triple W production, triple Z boson. So take the specific signal and then you say that, okay, these are my true negatives. So this is still not 2A compared to the LHC energies that, okay, B prime, how much it is your B prime mass. So basic point is that you can see that two jets are really overlapping only when you see the jet is extremely busy. The event is extremely busy with many jets.
Thank the speaker. Thank all the speakers in this session. It's very hard for us. Next one is